In this video, I'll be going over the sum and difference of squares, as well as some practice problems on these types of problems, as well as dividing complex numbers. Before we get started, go ahead and just do these two review questions. So pause the video and do the two review questions here that are above that line that I drew, and then let's see what you get. And here we go. So here for both of them, we are going to go ahead and just use the box method, right? Because we're multiplying two, here in this case, binomials. So I've got x and positive 6, x and negative 6. Notice how this is our difference of those two squares, right? I've got x squared, 6x, negative 6x, and negative 36. Then notice how the two x terms, our like terms, cancel out. 6 minus 6 is 0. So all you're left with is x squared minus 36. And there's our difference of two perfect squares. Now we've been going over our complex number operations. So again, we are multiplying two complex numbers here. Notice how that we discussed this a little bit, that we are multiplying two conjugates because the signs of the imaginary parts have been changed. So here, let's see if you remember the type of answer here in this case that you would get, but we're going to now be multiplying our full complex numbers, but with x now. So x and 4i and x and negative 4i. So here now you have x squared, 4ix, so we'll kind of go over that here, negative 4ix, and then here you have negative 16, but I times I squared. Now, notice how these two terms here on the diagonal are like terms. They're both imaginary and they both have x. So here I can combine them. Well, 4 minus 4 is just 0. So these two like terms cancel out. Notice how, just like before, right, we have I squared. We can't leave it as is because I squared is negative 1. So multiplying that by negative 16, you now have positive 16. So now we can write this as x squared, right? So from our top box here, but now plus 16. So notice here when we were multiplying our two good old binomials, we ended up with a difference of two perfect squares because we're subtracting, versus in this one, we multiplied two complex numbers with our two imaginary parts here, and we ended up with a sum of two perfect squares because now we ended up adding. So here, what we're going to be focusing on is the factoring. So here, if I'm factoring to the difference of two perfect squares because we're subtracting, that's the same as how we would before, just use the square root of each value. So this would be x plus 3, because the square root of 9 is 3, times x minus 3. So then here, that means now if I'm taking the sum of two perfect squares, right, because now we're adding, and the square root of 9 is still 3. We're now going to write this as x but plus 3i times x minus 3i. So now when we are taking the sum of two perfect squares, we do need I in that factored form. Because again, here, that I squared will become negative 1. That's how the negative here becomes a positive. So first off, again, we always make sure that we factor out the GCF. So any case of factoring, is there a GCF? So as I go through here, first off, I see I have a sum of two perfect squares. So that means for the sum, I know I need I in my factored form. Now I don't have a GCF, it's because x here is just, our a is 1. The square root of 4 is 2. So I'm going to have x plus, not just 2, right, but now 2i, because it's a sum of two perfect squares, times x minus 2i. Now here we do have a difference of our two values here. So we do not need I, because this is just going back to the basics on our difference. But we do have a GCF. I can divide out that factor of 2, greatest common factor of 2. So same as before when factoring, take our 2 out here, right? That GCF. Now I have 9x squared minus 4. Now we can continue. So don't forget to bring down our GCF here, value of 2. Square root of 9 is 3, so 3x plus, well, the square root of 4 is 2. And then 3x minus 2, because remember, we're factoring the difference of two perfect squares. Notice here, we are again doing the difference of two terms here, so no y value now. There is no GCF because there are two terms here, or the values are 16 and 1. But we do have two perfect squares. The square root of 16 is 4. So 4y plus, well, the square root of 1 is 1. So 4y plus 1 times 4y minus 1. Now the last one, we do have a sum of two perfect squares. So with our sum of the two terms here that we're going to end up factoring, we do need I in our factored form because now we have the sum. And again, there is no GCF, but the square root of 9 is 3. So 3x plus, well, the square root of 64 is 8. But don't forget now we need 8i because this is the sum of two perfect squares. And then 3x minus 8i. So go ahead and pause the video, try these U-tries, and let's see what you get. So in the first example, our first U-try here, we had the difference of two perfect squares. So no I is needed. The square root of 81 is 9. So 9a plus the square root of 100 is 10 times 9a minus 10. Then here, the second one, you did have a GCF. You had to first factor out 3. Also, you should have noticed that this is the sum. We're taking the sum of two perfect squares in the end, so you do need I in your final answer. So here, take out that 3. Now I have 4x squared plus 9. Now we can continue our factoring. Bring down your GCF of 3. Square root of 4 is 2, so 2x plus square root of 9 is 3. So 3i, right? Because we need I in our factored form for the sum, and 2x minus 3i. So then here in the third one, notice how you had a sum of two perfect squares to factor. So we do, again, need I. No GCF. So this is just x plus square root of 144 is 12. So 12i times x minus 12i. Then the last one, you had to see which of these answer choices is the full factored form. Well, I noticed from test taking strategies that in the end, we're taking the sum of two perfect squares. So we do need I. So that means I'm not going to choose B or D because there's no I here. Then notice from the other answer choices, we do have that GCF of X. Use that as your guidance. Then notice how both terms do have that GCF of X. So let's take one X out. So X then time, we had 3 X's, so now we're down to 2 X's. Plus you had the 1X here with 49X, but we're taking it out from the GCF, so now just 49. Now you can, there is no other GCF here, so now we can continue. The square root of 4 is 2, so 2x plus the square root of 49 is 7, 7i times 2x minus 7i. So that's why here the answer was A. So for those who chose C, you forgot to take the square root of 4, which is 2. Now, this is just some practice and review on what we did previously with dividing. So go ahead and pause the video, try these 4 practice problems, and then we'll go through these. And now let's go through these 4 practice problems on dividing complex. Remember, you can't have I in the denominator, so that's why we always use the conjugate of the denominator to multiply both the numerator and denominator. So in this case, That is 7 minus 2i here because we need to change only the sign, right, of the imaginary part. But what we do to the denominator, we also have to do to the top, to the numerator. Notice here how we are just distributing our 12 to both of the values in our complex number. So 12 times 7 is 84. Then 12 times negative 2i, negative 24i. Then here you could do the box method in the denominator, right? Or we did talk about how you could multiply the terms to each other, right? Because 7 times 7 is 49. And then here you have 2i times negative 2i, which is negative 4i squared. Then remember, whenever we had I squared, that was negative 1. So this is 49 plus 4. So that's why we're always adding, giving you that denominator of 53. You can also write this final answer, right, as 84 over 53 minus 24 over 53i. Then for those, just to show you if you did box method, I'll go through and show box method for this one. So again, you guys can see that. So 7 and positive 2i, 7 and negative 2i. So here you have 49, 14i, negative 14i, and then negative 4i squared. And if you recall, right, from multiplying conjugates, the I terms, our like terms here, always cancel out because that's 14 minus 14. So they're going to always cancel out. Notice how what you're left with in the other diagonal, there's your 49 here, and then here's that negative 4i squared, which ends up becoming 49 plus 4 because I squared, remember, is negative 1. So that's how you get positive 4 and 53. Now in the second one, you should have noticed in practice that this denominator here was not in standard form. So I'm going to first rewrite this as 8 plus 3i still in standard form, but now over 6 plus I. So I'm just going to cross that out. That means the conjugate you were supposed to multiply by for the denominator is 6 minus I. Then we multiply to the same on top. Now you do have to do box method here for the numerator. So I'm going to set up our box here, our area model. So I have 8 and positive 3i and 6 and negative I. Now I've got 8 times 6, which is 48. Here, 6 times 3i, 18i. 8 times negative I, negative 8i. Then 3i times negative I, negative 3i squared. Then notice here you do have I squared, which is negative 1. So negative times a negative, positive 3 here. So I'm going to cancel that out. You also still have like terms to combine because we have our two imaginary. 18 minus 8 is 10i. So now with combining like terms, we have 48 plus 3. So 48 plus 3 is 51. In our numerator, we have 51, but don't forget your I term, right? The imaginary, so plus 10i. Over, so here we go. 6 times 6 in our denominator is 36. Then here, I times negative I is negative I squared. Now treat that as if this is a negative 1 here, right? Then I've got I squared, which is negative 1. Two negatives make a positive 1. So 36 plus 1 is 37. You can also write your final answer, right, as the two fractions. So 51 over 37 plus 10 over 37i. Then the next one, so number 3. It's already in standard form, however, the numerator was not. So let's go ahead and rewrite this so that the numerator is in standard form. So this is negative 4 plus 10i. Then over, still 5 minus 4i. So I'm going to go ahead and cross that out because now numerator and denominator are in standard form. We're going to find the conjugate of the denominator, which is in this case 5 plus 4i. Remember what we do to the denominator, we also do to the numerator. Now we can multiply our two binomials, so we do need to set up our box method or area model. Then, of course, if some of y'all are doing FOIL, right, that front, outer, inner, last, of course, you can continue using that strategy as well. So here, 5 times -4, -20. Here you've got 50i, -16i, and then here you have +40, but I squared. And again, I squared is -1, but +40 now times -1 is -40. So really, we now have -40. We also have our like terms here, our two imaginary parts to combine. 50 minus 16 is 34i. Now last to combine, -20 minus 40. So -20 minus 40 is now -60. So I'm going to write that here. So -60, but don't forget our imaginary part. So plus 34i. Then let's go through and use that pattern. So here, 5 times 5 is 25. Then here, -4i times 4i, -16i squared. Then again, I squared is -1. So that's why we're not subtracting 16, because a negative times a negative is a +16. So we have 25 plus 16, so making that now denominator 41. Then, of course, separate. You have -60 over 41. Sorry, guys, with my pen here. So -60 over 41 plus 34 over 41i. And with our last one here, our denominator is 7i. So the conjugate of +7i is -7i. -7i. So we're going to multiply by -7i. Here now, you're just multiplying 5 times -7i in our numerator. So now I've got -35i. Then in the denominator, that is 7i times -7i, -49. Oh, sorry, guys, with my pen here. Times, but I squared. So that should be -49i squared. And again, I squared is always -1. Negative times a negative is a +49. So -35i over 49. However, you can simplify this, right? Because both of these values can be divided by 7. So this here, you get -5i over 7. Sorry, so that's supposed to be -5i. So now the last 4 problems are, again, practicing more of that, factoring the sum and difference of two perfect squares. Notice how there is no x term, right? B is equal to 0. So go ahead and pause the video, try these 4, and then let's see what you get. And so with the first binomial here that we're factoring, this is a sum of two perfect squares, so you do need I in your answer. No GCF, but the square root of 4 is 2, so 2x plus the square root of 81 is 9, but because of the sum, don't forget our I value. So we have two complex numbers here, and then 2x minus 9i. But then number 6 is a difference, so no I is needed. However, there was a GCF of 4 that you needed to factor out. So 4 times x squared minus 100. Now I can go through and continue my factoring. So 4 times, well, that's just square root of x squared is just x. But so x plus the square root of 100 is 10. So x plus 10 times x minus 10. Then number 7, you are back to a sum. You're going to be factoring sum of two perfect squares, so we do need I again in the factored form. There was also a GCF of 2 that you needed to factor out. So 2 times x squared plus 36. Now we can continue our factoring. So 2 times x plus the square root of 36 is 6, but don't forget I, right? Because this is the sum of two perfect squares, so we need two complex numbers, times x minus 6i. Then the last one, this is just a good old difference of two perfect squares. No GCF, so here we go. Square root of x squared, of course, is just our x. Plus the square root of 121 is 11. So x plus 11 times x minus 11.